Okay, so thanks. And of course, I would like to thank the organizer for the kind invitation. It's always nice to be at ESI, in particular because I've been here now as a participant, as organizer, and finally also as a speaker. Okay, so what I will talk about is, as you see, some phase field topology optimization. And in particular, this is a series of works that been done together with Ulysses Stefanelli, who is from the University of Vienna. Okay, so just a brief introduction about something that you probably already know from all the talks that we had during this meeting. So what I mean just by topology optimization, so you're given some design box. So here is just a square for simplicity. And you want to distribute some kind of material that you know a priori, let's say. And you've given some data. So here you have, for instance, a boundary condition W, an applied force is a volume force, and then a Neumann part of the boundary. Yeah? And what you want to do is to find the best distribution of the material in order to, let's say, maximize performance of the resulting object. Okay, and this is of course an optimal control. So they are known, or if you want the control, the variable is the subset E where you will distribute the material. And your, let's say, constraint to the problem is the physical properties. So let's say the physical properties that we'll consider here. So what we will start from is actually elastoplasticity. So this, at the end of the day, would be an evolution problem. Yeah? But we will actually start from an equilibrium. While in the second part of the talk, I will have only elasticity and, let's say, the interplay with microstructure. So it will be only an equilibrium problem. Okay, so I think that elastoplasticity was not recalled during this meeting. So I will start a little bit with the modeling. So they said we care about the distribution of some material. So let's say as a starting point, we talk about characteristic functions. So let's say the material or where you will distribute material will be described by the set where z, some variable, scalar variable is equal 1. While where z is equal 0, you assume to have the void. So the void would actually destroy completely your problem in the sense of coercivity. So you assume that you have some kind of ersatz material, so you're still coercive, but maybe, let's say, you are as close to 0 as you wish, yeah? But still not 0. Good, so this is for the description of the, let's say, the distribution of the material. So the point is, let's say, elastoplasticity. So we work in a linearized setting, and just to have a round energy, you could say, we work also with hardening, yeah? So that everything is described in terms of functions and there are no measures involved. In particular, as if you are an expert, this plastic strain is a function, is not a measure, okay? So the quantities that play a role here are the displacement U, so a function from the box, the design box omega into Rn. And then you have epsilon and p, these are the elastic strain and plastic strain. And since we are working in linearized elastoplasticity, you have the usual constraint that the symmetric part of the gradient of U has an additive decomposition, so is the elastic strain plus the plastic strain, okay? So the energy that you define then given these three quantities is written here. So is the elastic part plus the plastic part. So since we're working with hardening, you have also a quadratic term in the plasticity. So here C and H are simply elasticity and hardening tensor. So they are known and they are function of Z. And as I said here, there is the hypothesis of this ersatz material. So you're basically saying that C and H are positive definite and they are uniformly far away from 0. Let's say here we are preparing already the phase field modeling, so for every z in the interval 0, 1. Okay, so even if you are in the void region, you're not singular. So these two quantities are positive. Okay, and since we're talking about plasticity, I also need some normality rules, yeah, some flow rule. So the point is that I'm starting from the equilibrium problem. So here I'm using, let's say, one example is the von Mises rule, von Mises criterion. So you have that this variable has to be in the subdifferential of P of the modulus, let's say, computed in P. And what you have here in front is d of z is the yield stress, is also assumed to be a function of z, just for completeness. You could also assume it to be constant. You might say in many of the applications, this could be also just assumed to be a constant function, okay, something known. And again, you are assuming that this is strictly positive, far away from zero in the interval 0, 1. So as I said, let's say plasticity would call for an evolution problem. So what you would like to see here is actually P dot. But we start from an equilibrium problem, and then we will see later on that, let's say, the fundamental step is to know what happens in the equilibrium, and then we can pass through an evolution problem somehow, in some sense. Yeah, I will try to convince you later on that this is, anyway, the most important part. Okay, so this is all the physics that you have behind this, let's say, the topology optimization problem. And so we can see, let's say, how you set up an example of the cost energy, the cost function. Okay, so here I recall simply the set of admissible pairs or triples. So here, let's say you are given the data of the problem, so the force, the two applied forces, and the boundary datum A, W, which is an H1 function in omega. And the triples, okay, is given basically by what I described you before. So here you are saying you have the additive decomposition in elastic and plastic part, and then the boundary data. Okay. So the possible target function that you can cook is, for instance, let's say, minimize the compliance. So let's say the reaction to the applied forces. And here, maybe you have to describe a little bit what is this L in front. So the easiest possible case is that you take L equals Z. Okay. Here we want to regularize a little bit. So you say L is not exactly Z in 201, but it's something a bit smoother that is connecting anyway 0 and 1. Okay, because at the end of the day, you want to take derivatives here. And the last term instead is simply a perimeter of the set where Z is equal 1. The constant is not important. I mean, it's 1/6 simply because of the choice that we will do later on in the phase field problem. And let's say what you are saying here is that you don't want anything homogenized. And since homogenization would pay a lot in the perimeter, when you add the perimeter, you will simply stay in the set of finite perimeters. So in particular, you will have, let's say, apart the existence of minimizers, anyway, something that is really a set. Okay, you don't end up in homogenization effects where you have a material that is somehow staying in between 0 and 1. Okay, so instead the physics is described here by the energy and the dissipation potential, let's say. So the energy, as we presented it before, so elastic and plastic part, and then you have the applied forces. So the work time by the applied forces. And then the dissipation potential is the one given by the von Mises rule. So it, let's say, is a weighted L1 norm at the end of the day. Okay. And in particular, this is somehow the problematic term later on, let's say, since this is not differential. Okay. Good. So here is the problem that you set up. So you want to minimize this cost functional J in the class of BV function. So, or if you want, the class of set of finite perimeter. So BV taking values in 0, 1 only. And the physics is described by the equilibrium problem. Okay, so you're saying that let's say this displacement U that is appearing here is part of the tripole that is solving the equilibrium elastoplasticity problem. Okay, so you minimize the energy E plus D given Z. And in particular, you can say, since you are working in the hardening case, actually, this problem is strictly convex, so you have a unique solution given Z. So at the end of the day, this functional J is only dependent on Z. Yeah? So U is a function of Z, you know it. You don't know how regular it is, but it's given. And okay, of course, you can given the data, you can always find a solution of this problem. This is just an application of the direct method of calculus of variation. Actually, this function U is for sure is even continuous with respect to Z, even more. We will see it later on. And the problem is that we would like to give some kind of optimality conditions. So at this point, I would say that there is a problem in working with sets of finite perimeter, in the sense that I don't really know how to find or how to describe the variation. In the sense you can do the variation of the perimeter. This we will see also later on in the microstructures problem. The point is that, let's say, since you have this admissibility condition, this is not clear how it changes when you do compositions, okay? So you could say gradients are going with gradients, but these eta and q, that are the elastic and plastic part, are L2 functions, and they will behave as they want to behave. So it's not really clear how you can differentiate later on. Okay, so that's why, I mean, from my point of view, it is nicer to work with a phase field approach where the variation that you can take are more standard somehow, in the sense that you can take outer variations, so simply sum up functions. And so which is the model that you take now? So let's say the idea is simply that instead of having a sharp model where you take z, taking values only 0 or 1, you allow also for some kind of gray areas. So where z will take values in between 0 and 1. But then let's say your function has to say that in most of the region, of the design region, you will take values 0 or 1. And this is encoded in this last term here. So delta, you have to think that is very small. Here you have a double well potential. This is just a choice. And since delta is very small, z will always be either 0 or 1, very close. Yeah? And then, again, since delta is very small, you allow for transitions. But let's say a transition have to be small enough. Let's say of order delta, and this is again encoded here. So since delta is small, you are allowing for some kind of transition, but it will be small enough. Okay, and this, let's say this is simply the approximation of a perimeter given by the modica morta that you've seen also yesterday. Okay, so this is the new cost functional. And at this point, you can, of course, say, I want to minimize this kind of approximate problem. So I minimize now this new functional J delta, and the equilibrium condition is still the same. And of course, you can prove that there exists a solution. And moreover, okay, this is simply a gamma convergence result, or is a, let's say, a consequence of the modica mortola, is that whenever you have a sequence of solutions of this problem, P delta, you let delta go to 0, and you will converge to a solution of the original problem. So this is simply saying that is a good approximation of the problem, of, let's say, the initial modeling, okay? But at this point, at least with this, I know how to do variations, almost, in the sense that, okay, J delta is as regular as I wish, so here there will not be any problem. But here there is still a singularity given by the dissipation potential. So this, I said, is an L1 norm. So let's say if I want to differentiate, I will have a nice subdifferential, but not really a differential. And I want to play only with differential. Okay, so this is why actually to find some optimality conditions for this problem here, I want to first to regularize this and then pass to a limit in the regularization and see what I will have at the end of the day. So this is what you can do. This is, let's say, one possible regularization that you can take. I think the simplest possible one. You're simply removing the singularity in 0, okay? By adding this 1 over gamma, and then you will let gamma go to infinity. Okay, so the new regularized dissipation is this one, of course. Let's say it's not really a dissipation if you want to think about rate-independent systems, since it is not one homogeneous. But let's say it is convergent, of course, to the original one. Okay. So the equilibrium problem again is not so much of a novelty, but let's say you can solve, given delta and gamma, you solve this problem. So this is what you are actually working with for later on for the optimality conditions. And whenever you take Z gamma solution of this one, you say you let gamma go to infinity, you will solve and you will find so you will approximate a solution of the phase field problem. Okay. But now with these, I can work directly. So what I mean by this is that if I want to find optimality condition for this problem, in particular, I can work out the differentiability of the control to state operator that is behind this, let's say, the constraint to the minimization problem, okay? And this is what is written here. So you can prove that this function here, that is simply associating to a phase field variable. Let's say here in general is taken as a function in infinity, the equilibrium tripole. This is now Frechet differentiable. So there is just one little problem, let's say, that is in the data of the problem. So in order to ensure that you are differentiable, you actually have to add a little bit of regularity. So p equal 2 was enough for all the results that we've seen up to now. So the phase field approximation, existence of optimal distributions. But if you want a little bit of regularity, so let's say differentiability in this case, you have to assume that everything is p integrable. So f is LP, g in LP, and w is w1p, or any p that is larger than 2. So, and what is behind here is basically regularity results. So let's say what is saying, what you have with given this better integrability is that you get a better integrability also of the function u. So u will be w1q for q that is slightly larger than 2. You don't know how much large, but you don't care. This is enough. Okay, and it's enough to then to write down, let's say, this kind of problem. So what happens when you differentiate? Well, basically, you take a derivative in some direction phi. You find out, let's say, some kind of intermediate optimality condition. So let's say you find that this function here is differentiable, and in particular, the derivative is given by this kind of, let's say, tripole is still an elastoplastic tripole, in the sense that you can say V is a sort of displacement, eta and Q are elastic and plastic part of the strain. So the problem that you see here, not so nice, but at the end of the day is a sort of elastoplastic problem still. And you see here why I need a regularization. So here I'm taking a gradient of H gamma, and here I'm even taking an Hessian, so a second derivative. Okay, so this is why you need to regularize the function at the beginning. Okay, so of course this is still depending on the direction of the phi of where you take the derivative. So this is not really an optimality condition. This is an intermediate step, but let's say as a corollary, you can get the optimality condition simply by passing to an adjoint system. So what you say is that at the regularized level, let's say there exists some adjoint variable, this adjoint tripole here. And the optimality conditions are written here. So the first one, let me see, yes, it is already the problem for this variable here. So it's a sort of elastoplastic system, similar to what you've seen before. Simply, this is not depending on the direction of the derivative anymore. And the second one instead is the optimality of the cost function. Okay, it's simply, if you remember what the cost function was, you just take the derivative and play around with the adjoint system. So basically with this system over here. Okay, so this is, let's say, what you get for gamma finite. And in particular, let's say, here is everything that you can write explicitly, let's say, in a sense. In the sense that this is P gamma, you know, is a solution of the approximate problem. And so let's say this is the problem that you're writing here. Okay, here is written in terms of PDE, but you could also write it in terms of a minimum problem. Okay. A bit more complicated when you pass to a limit in gamma. So you go to infinity, you said, I will approximate a solution of my phase field problem with no regularization on the dissipation potential. And let's see what remains of the optimality conditions. So the first two properties here are I'm simply rephrasing the elastoplastic equilibrium. This is equivalent to the elastoplastic equilibrium in terms of minimum problems. So this is nothing new if you are familiar with it. This is exactly the behavior of the plastic strain. Okay, it's not active whenever you don't reach the yield stress, and whenever instead you have this rho is equal or larger than D, you will have some plasticity. Okay, what is a bit more interesting is what happens to the adjoint variables, so to the optimality of the cost functional. So here you see what remains again of the adjoint variable. So this is similar to what you've seen before. Is a elastoplastic tripole with, okay, this 0 means that you are solving a problem with 0 boundary conditions. Maybe I should have said it also before. And instead, there is another field here that is pi, is in L2 with values symmetric stat deviatoric. So it's somehow, again, a sort of plastic strain that is surviving. And this is somehow the limit of what was here, what was written here, okay? Somehow the limit of this Hessian here, or Hessian times P bar, okay? So somehow this is again saying that the tripole U bar, epsilon bar, P bar is solving a sort of elastoplastic system. But here you have an additional variable pi, okay? Then you have the second one is simply the optimality of the cost functional. And finally, let's say the third set of equations or inequalities is telling you that, let's say, this pi is not really a random space. So here you have that is orthogonal to P, but P you know because you solved the, let's say, the optimality problem. It lays in the same half space of P bar. And finally, here you have that somehow P bar is behaving more or less as a plastic strain, in the sense that it is not active whenever rho is, let's say, whenever you are below the yield stress. Okay, so it behaves more or less as P behaves. Good. So, and this, I think, concludes the problem for the static case. Okay, and let's see instead what we can do or what we've learned in order to solve the evolution problem. So the evolution problem, let's say, since we are talking about elastoplasticity linearized with hardening. So here we work in the setting of rate independent problems. So I don't care about inertial effects. So you can write, for instance, the elastoplastic system in terms of a PD, okay, up to a sign, as I see here, because probably this is not consistent with what I wrote in the first slide, but let's say it's not so important. So here you see that you're writing simply the equilibrium of forces. Then here you have the flow rule, and here this is what you want to see in an evolution problem. You have the von Mises with P dot here. And then, okay, just for simplicity, I'm saying that at the boundary I'm putting everything to 0 because otherwise it would be too long to write all the formulas. So here I have boundary datum is 0 on the Dirichlet part of the boundary, 0 Neumann on the Neumann part. And actually, I will also fix initial datum as everything equals 0, okay? Just for writing much simpler properties, much simpler formulas. And so the point of this kind of evolution problem is that this system is actually equivalent to an energetic formulation that comes from the rate-independent systems or rate-independent theory. So what is the energetic formulation? So you're saying that for every time this tripole here, that is the, recall you is the displacement, elastic strain, and plastic strain, is actually solving a minimum problem. And with this minimum problem, apart from this P of T that appears here, is exactly the equilibrium problem we have seen before. Okay? Before you would have had only Q here, so here you have Q minus P of T. My claim is that this is not so much of a difference. Okay, and the second property that you care about is instead energy dissipation balance. Okay, so it's saying that the energy at time t is equal to the energy at time 0 plus the work done by the external forces. The energy at time 0 is 0 because I'm saying the initial datum is equal to 0. And this equality is true up to the dissipation that is due to the plastic part of the system. Okay, that is due basically to this flow rule here. Okay, and what is nice about this problem, as I said, is that, or about this formulation, is that here you are working with equilibrium problems. The equilibrium problems is exactly what we've seen before. Okay, and this is in particular, in my opinion, or just as I learned all this business, is much better to work with this kind of problems because they are somehow derivative free rather than working with PDEs, even if they are totally equivalent at this stage. Okay, So you can set up your problem. Let's say you want now to minimize this kind of cost functional. It's similar to what we've seen before. So let's say the modica mortola part is exactly the same. What changes here is that you have to somehow work with a sort of compliance that evolves in time. So the compliance you take care about, for instance, is the, let's say, final compliance, okay? And then you have whatever was spent by the forces during the evolution. That is actually also what appears here, okay, in the energy dissipation balance. Okay, so for instance, you can minimize this kind of functional under the, so with respect to Z, under the constraint that, let's say, now this tripod is actually solving an evolution problem. That was the one that we have described before with the energy formulation, okay? And once again, maybe it is worth to say that at this stage, so when you work again with hardening, elastoplasticity plus hardening, actually given Z, this evolution tripod is unique, okay? So again, this is only a minimization in Z. You don't really, I mean, you care about U, about this, the displacement U, but it's again only a function of Z, okay? And at this point, okay, as I said, you can say that there exists a solution. Again, this is just an application of the direct method of calculus of variation. So I think that if I, yeah, for sure, if I remember correctly, but let's say U is actually continuous with respect to Z, is even better, because we can also find optimality condition later on. And what we are interested in is exactly optimality conditions. So in order to find them, let's say we have a rather typical way to approximate rate-independent systems, which is, let's say, discretizing time, find or solve some kind of equilibrium problems at the discretized level, and then pass through a limit with time. Okay, so you try to repeat the same idea for the optimality conditions. So what do? You discretize time. So here is tau k is simply the time step. You define your time nodes. So it's I times tau k. It's not so difficult. And you discretize also the applied forces. So this is, let's say, the force F computed at the time that is given by here. It is given here. So TKI. Okay. So you have a sequence of discretized energy. So nothing changes. It's simply that here you are replacing the force F with the force computed at time TKI. So your approximate discretized force here. And then you say, how would you construct a solution solving, let's say, the stability or the equilibrium condition and the energy dissipation balance? As I said, you would solve this kind of equilibrium problem and then pass through a limit. Okay, so define some kind of interpolation and then pass through a limit with interpolations. And as I said, this is only an equilibrium problem. In particular, you have to say that, let's say, whenever you solve at time TKI, this is a quantity that you already know. So this is exactly an equilibrium problem. It's exactly the equilibrium problem we have seen in the first part of the talk. The only difference is that, let's say, is not this function is not centered in zero. Okay, but if you believe that you could differentiate the other one, well, you can do it also with this kind of equilibrium problem here. Okay, good. So what you do, let's say, you set up a topology optimization problem. Let's say an optimization problem for let's say a time discrete functional. So here, let's say this additional index k is simply saying that instead of taking the force F, I'm taking this kind of interpolation here, but nothing changes really in the functional. The point is that for this problem here, I can find the optimality conditions, and then, so which are exactly what we've seen before, and then I can pass through a limit in the time discretization. Okay, and what do I end up with is this kind of result. So let's say these first two conditions here are simply, again, rewriting in a third equivalent way the elastoplastic system, okay? So I can write it also in terms of variational PDEs. Here I forgot that this G should be equal 0, but okay. So this is the equilibrium condition for every instant of time. Here again, you have the plastic flow rule somehow. So you're saying that P is not varying whenever you don't reach the yield stress. Otherwise, this P dot will be probably different from 0. Okay. And what is a bit more complicated is the behavior of these adjoint variables here. So now you have U bar, epsilon bar, P bar that of course are depending on time. You see again this guy pi that again is a function of time. And so the first system, the first equation is again of elastoplastic type. Here you see the optimality of the cost functional. Of course, this has to be written now with additional integration in time. And here is what remains, let's say these two equations is in that instead what remains of the, let's say, description of pi and the P bar. Okay, so here you can still say that P dot is, that pi is orthogonal to P dot. Okay, before it was pi orthogonal to P. And here instead you would like to say something about P bar dot being 0 whenever this rho is not in the yield stress, so something similar to this, but for P bar. You cannot do it because now I cannot prove really a regularity in time of P bar. Okay, but let's say this is a sort of weaker condition that is similar. It is actually somehow, yeah, it's somehow similar or a weaker form of the same property. Okay, and this is let's say everything for the elastoplastic problem. Okay, and I would like instead to pass to, let's say, a second application that is topology optimization in the case of microstructures. So here we go back instead to elasticity only, linearized elasticity. So we don't care anymore about plasticity, and we have still a phase field approach. The idea that you have in mind, that you can have in mind, yes, is that, let's say, in your design box, you can distribute a certain material that will still be described by a phase field function. But on top of that, you can somehow distribute also a sort of microstructure. You want to see if, let's say, you can distribute some kind of periodic microstructure inside your design box. And maybe, let's say, somehow reinforce the material. Okay. So this is done actually in this case, in the simplest possible form, okay? Just to see somehow what happens. So here now what it was before Z is actually called phi, okay? So this is somehow the macroscopic behavior of the material. So how you macroscopically will distribute the material. And then instead the microscopic part is here denoted by M, okay? This M is assumed to be periodic on Y. Here Y is simply the unit square. Okay. So it's a phase field approach, which means that phi and M are both H1 functions. So here for simplicity, you're saying, let's say phi is the distribution of the material, so it's exactly behaving as I said before. And here M is a sort of reinforcement, so it's not taking values in 0, 1, just you choose that it takes values in 1, 2, for instance. Okay, but it behaves exactly in the same way. So here, what you're saying with this kind of energy is that of elastic type, of course, is that you're mixing somehow two possible elasticity tensors. Okay, so let's say the idea could be that the C2 would be the elasticity tensor associated to the void or ersatz material, so it's still positive but very small. And is active only when phi is equal to 0, okay? While C1 is the, let's say, the elasticity tensors associated to the material you want to distribute, and somehow you could reinforce it because you are adding some microstructure, okay? That is still a scalar function at this point. Okay, and what you want to optimize is this kind of functional here. So again, you have the compliance part of the cost. And then what you see here is simply, again, a sort of modicum orthogonal, okay? It's done both in the variable M and in the variable phi. So here I think there is an average over omega missing, but it's not so important. But anyway, what you have to keep in mind is that M is, as I said before, is periodic on the unit cube, okay? And okay, and here in the set of admissible distribution, you are also saying that you have maybe some kind of volume constraint. Okay, you cannot distribute so much material, so V is here fixed, and W is also fixed, and you cannot even distribute so much of a microstructure because maybe it's costly. Okay. Good. So the problem that you set up is, of course, this one. So you minimize your cost functional. And it's subjected to the equilibrium, the elastic equilibrium, okay? Where I recall that this energy here is written, up here is the elastic energy, minus the applied forces. Okay, so of course there exists a solution. What I care about is somehow, again, optimality conditions. And in particular, so let's say at the phase field level, you can do exactly the same that you did before. It's even simpler because you don't have plasticity. But what I'm a bit more interested about is the behavior when you pass, let's say, to the homogenized and sharp limit problem, let's say. So let's say you send epsilon to 0. What you expect is that you will have a homogenized problem because here you're distributing something that is, let's say, with a periodicity. And the second point is that if you send epsilon to 0, then you will end up also not anymore with a phase field problem or with a sharp interface problem. So these will become perimeters. Okay? Here I forgotten to say, but H is a double well potential. So simply is 0 only if this zeta takes value 0 and 1. So it's the same as before, just a bit more general. Okay, so what you end up with is, again, very much traditional. This modica mortola. So let's say plus, let's say there is an ongoing homogenization, okay? So what changes is that, let's say the cost functional is again the compliance plus the perimeter, the sum of the two perimeters now. And what changes, of course, is the elastic problem. So here, let's say this C star is a homogenized tensor, okay? And how you find it at the end of the day is by to-scale convergence. If you are into the topic, you know what it is, otherwise just believe me. Okay, and how you define C star is given in terms of correctors. These correctors are, of course, functions of phi and m, also on phi and m. So the problem is that when you want to solve then this problem here, you have to take care of the regularity of C star with respect to phi and m. And the regularity of C star comes from the regularity of the correctors, okay? And since they have, at the end of the day, a variational characterization, actually you can prove that they're continuous, they're even better, you can even differentiate. And so that's why at the end of the day, you can find also some kind of optimality condition. Okay, just to describe a little bit how you find the optimality conditions. So here, I'm working in the sharp interface problem. So what I want to do here is what I couldn't do with plasticity, that is take variation of the perimeter. Okay, so this is just the gamma convergence, but I talked to you, I said about it already. So the variations that you take are the following. So you have to do two variations at this point because you have two variables. So the first one is the variation in the variable phi, that was the macroscopic distribution of the material. And okay, here is how you construct it, but simply you take some field phi and you solve this typical flow system. And in this way, you define, let's say, the transformation that will give you the inner variation or the variation of the perimeter. You do the same at the level of M. So this is the microscopic distribution. Okay, so in the periodic cube, you do a variation for M as well. So it's the very same idea. It's simply two different systems. And you end up with a optimality condition that is horrible to see. But let's say this is the optimality of the cost, I would say, yes. And so what is the point? So let's say what is worth to mention is that here you have two Lagrange multipliers. Okay, these are due to the volume constraint that you gave to your problem. Okay, so they're active, of course, only when you touch them. So only when you distributed exactly a certain amount of material. And so here you have these two terms that are exactly the variation of the perimeter. So this you can find also in, let's say, in they are traditional, let's say, they're classical somehow. And what is a bit annoying to find out is this C tilde here that comes from the fact that at a certain point you have to differentiate also the elastic tensor. Okay. So this you can see somehow in the technique that you used to prove. So it is, of course, simply try to differentiate this kind of the cost functional, this function for t equals 0. Okay. And what are here phi t and mt are defined here. So it's phi compose the inner variation that you defined before. The same you do for mt. And u of t instead is the solution of the elastic equilibrium given phi t and mt. Okay. And here is where you realize, of course, that in order to find this kind of derivatives, you have also to differentiate the elastic tensor. Okay. And this is where somehow you have to work out all the details about the properties of the correctives. Okay. So you can prove at the end of the day that this is differentiable and in t equals 0, and its derivative is indeed given by the C tilde that you've seen in the formula before. Okay. And so with this, I think I concluded. Yeah. So I thank for your attention. Yeah. Okay, but you mean also in the design of the optimal control problem itself? This we didn't think about. It's definitely interesting because it was also done something similar by Allaire, not with the phase field, but no, we didn't think about it. In the sense that if you see here, M, of course, is only scalar, so you're only saying I'm reinforcing somehow. Of course, it would be interesting to see. I'm not totally sure how much it would change from an analytical point of view, in the sense that, yeah, apart, of course, the fact that you have, how you design the modica morta is the point, yeah? Because then it becomes vectorial. Yep. Yeah. Ah, yes. So how you prove the proof in the equilibrium, the evolution problem? No, of course it goes. Yeah, that's the point. That at the beginning I thought once you have the equilibrium is done. Instead, you have to, if you want to do the evolution problem, you have to go back again to the gamma, find some nicer controls, and then proceed first with the time discrete, and then to the evolution. Yeah, so somehow you go first discretize time, and in the time discrete, you again regularize. So there you have some optimality conditions for the regularize, and then you try to pass them to the limit. So somehow you have to really to go back multiple steps. But yeah, let's say the point is that when you do once you learn the equilibrium one, it's not too different to do also the evolutive one. Mm-hmm. This is something I didn't really understand. It was a question that he had at the beginning. I got stuck somewhere in the sense that I probably just my problem of understanding of the stochastic homogenization. I would say yes, and it would be also the a bit more interesting in the sense that you say I could have, of course, errors in distributing the material, and this could be encoded in a sort of stochastic behavior. Yeah, of course. I mean, when I will actually really learn what is going on there, then I would say yes, I will be able to do it. Yeah. Yeah. Huh. So I'm not totally sure in the sense that the only reference that I know is the if you want the book by Allaire, and is the homogenization method. But there they always work with some theta that is a density and is in between 0, 1. And then the problems become more like how can I approximate something that I find as an optimal distribution with something that is actually only 0, 1. There's somehow more recovery sequence if you want. So without the perimeter constraint, I would say, I mean, if I don't put anything, I really don't know. I don't know which kind of additional constraint instead you can have instead of the perimeter in order to. But then you would have, I mean, I guess yes. But the point is maybe it has to be something different in the cost function itself. I mean the constraint. I don't think it is a property of omega itself, because even if I work with something super regular or convex, I don't think this will have really an influence. So either you take something different here instead of the compliance. This will keep, you think? Yes, no, physically, yes, but I'm thinking if this is enough to enforce you 0, 1, I think this is it is too weak, maybe.